Let's start. So let me maybe spend a few minutes trying to indicate the idea of the proof of the theorem that I stated last time. At least one step, yeah? Yes, yes. So last time we stated the theorem about the kind of surprising compatibility between monodromy of quantum connection being equal to or isomorphic to the action of pi 1 on the K group, equivariant K group of our variety. And yeah, we in the last talk I discussed how to construct a section of pi 1 on the category, and this construction of quantum connection was discussed in other talks, in the Verses in particular. And again, using some ideas that were mentioned in Andrei's talk, one can make use of the following observation. And so idea. Well, we basically, again, all these proofs are sort of computing both sides. So we can hope for a more conceptual proof in the future, but but for now we just characterize the answer in both sides. And characterization proceeds along the following lines. That okay, so basically characterize or compute the parallel transport, the isomorphism between two K groups of two resolutions corresponding to two different cones, which corresponds to the path connecting them via an Elkov, well, A. So again, in the first talk I mentioned these points of one kind, of two kinds, and so this is, so here we have some cone, so this is this V plus IC, and there is some other cone somewhere here, V plus IC prime, and so there is this real kind of part of our vector space sitting somewhere in between. So this is like on the poster, and this is somewhere else. And so we pick, so there's an A here, and well, there is this path just connecting them this way. And well, it's a compute, so this is done, well, the answer is the identity matrix, but I just need to explain the basis. And yes, yes. So in other words, I'm saying that this equivalence sends so I can right away state the key property maybe let's have this temporary notation that this is phi A to dB co of x c prime. So this equivalence, it sends a stable envelope. I mean, so yes, the key property is that it sends stable envelopes to stable envelopes, and this characterizes it uniquely. But again, this concept may be in slightly different context, was mentioned in Andrei's talks. And so how does this A enter the picture? So stable envelope is a construction which depends on a parameter, a stability parameter. And so so in fact, to make this sentence complete, I should say both here and here that these are stable envelopes for stability parameter, for stability parameter in A, maybe lambda in A. Yes.
Some questions.
Yes.
So stable envelopes are defined for one parameter subgroups, right?
The whole point is fully independent of that.
Yeah. So we okay. So that we work with yes. So maybe one important point here is that to simplify discussion to save time, let me assume that we have an at least for now, assume that x t is finite, or x even A where A is. So then I pick one parametric group and define category OR, and then this is an auxiliary choice that doesn't enter the theorem and enters the proof. And maybe in the end I'll say a couple of sentences of how to do it in a more general case.
Now, the second question is that you upgrade your equivalence to equivalence situation.
Sure, yes, because and this is again. I mean, as I already said. Yeah, good point. From the perspective of building equivalences, this is basically the same price. But yes, for running this argument, it's important to work with in the equivalent category. Yes, and so before I actually want to say a few words about what these are, but
We're talking about stable envelopes as we define homological, not k-theoretical reality.
no, of course I need them k-theoretically, and moreover I need them categorically. So maybe I should say categorical stable envelopes. And the definition, well, I mean, I don't know, I think Andrei mentioned this, but maybe he didn't explain the definition. No, but I mean, if you remember k-theoretic definition, then you can just make the same definition in derived category. But I will maybe say a few words about it in a minute. Well, for now, how to, whatever the definition, how to prove this property. Well, I mean, this occurrence is defined as a composition, you know, going this way and going this way. And so we have, by construction, dB co of x c going to dB co of this non-commutative resolution, which I discussed last time, but maybe didn't fix notation for it. Let's write this AA. So this is the abelian category, I mean, non-commutative resolution whose construction I discussed yesterday. And then dB coh of x c prime. And the key point is that the first arrow sends stable envelopes to Verma modules, and then the Verma modules go to so I mean, I don't know, let's call this psi and psi prime, and
So is it true because for every step you're going, because when you have your path to infinity, you go from one arc to another arc.
no, but at this stage we only work with one Elkov. We work with two combs, but only with one Elkov. That's the whole point. In a way, this is a relatively new idea in this old project. So we have this phi a is the composition of these two letters, and then this psi sends a stable envelope. So stable envelope corresponds to a fixed point.
So this parameter lambda is an A or Lie algebra A?
What do you mean? A is an Elkov.
Elkov, okay.
Oh, sorry. Yeah, it's not a torus. It's not an Elkov.
Okay.
Sort of. A, so it goes to M x. So this is Verma module. And this goes to, again, stable.
The Verma module is something defined globally, or how do you?
Yeah, just induced from.
So as a global, not as a sheaf or anything.
Yeah, it's defined. Yes, yes. In this sense, global. Yes. Maybe just one word. So again, so these are the categorical stable envelopes. And just to give one to say something about their definition, and so it's characterized.
What are you
Huh?
defining? The many objects. You give a definition of which object.
Of the stable envelopes.
Okay.
Well, Verma modules, at least in the algebra case, they're familiar, and and in general they're similar. So it's characterized by the following. So again, so we have this attracting locus, and so have a fixed point. And we have, so as Ivan pointed out, we actually have here an implicit choice of a generic one-parametric subgroup. So we work with attracting sets of this one-parametric subgroup, and this also defines an order on the set of fixed points. And stable envelope. Yeah, I will not write specific formula. I'll just give the flavor. So it's supported. So this is a pure geometric definition. So on. Yeah, it's an object in the. A priori, it's defined as an object in the derived category of coherent sheaves, and sometimes it is a sheaf, but I think we don't really use this. Yeah, no, of course, yes. Yes. So it's supported on, so for every fixed point, we have the attracting set, and then, so we can write the union of these attracting sets for all y less or equal than x. And so by definition of this partial order, this is a closed subset, closed Lagrangian subset. And and then there are two kind of properties one requires, and that well, the properties will say something about the behavior of this guy in the neighborhood of each fixed point, and in particular in the sort of near x, it's just well, just a line bundle. Yes.
The support only depends on not on the alcove, but on the chamber itself, right?
Yes, the support is independent on the alcove, and the first axiom is also independent on the alcove. Yeah.
Can I answer simultaneously to your last question?
Yeah.
The whole point of this construction is will be independent of the cone.
Of course, yeah.
This is how we're going to use it if the fixed points are not isolated.
Yeah, yeah. Yeah, I mean, this is kind of leads to this R-matrix construction. I mean, what you just said leads to this R-matrix construction and stuff.
So you said dependent or
Independent.
But as a construction with non-isolated fixed points is going to work only for equivalent.
Yes. The multiplex resolution does not isolate fixed points which are not polarized.
We'll negotiate about the plane.
Wait,
Ah,
sorry, then I'm confused.
It's hard to follow.
Okay. So, is the question?
So yeah, so you're not yet defining the map psi. You're defining for now. You're defining what the stable.
No, everything was already defined, and so this is a characterizing property. So in a way, logically, your question is not relevant, but in essence, it of course is relevant. And
So I just reading like psi is a map from STX to STX. The way you wrote it.
No.
what?
These maps.
Is this better? Yeah.
Yeah, I guess maybe I was asking. So in cohomology, then the stable envelope depends only on a chamber. And here you're saying that it depends on an alcove, or you're about to say it depends on an alcove. Right?
Let's finish listening definition.
Yeah, because I think K-theoretic envelope depends on an alcove.
Let's listen definition.
Okay, so near X is an explicit line bundle, and it is independent of A. So the key kind of axiom is that if you consider this sheaf and then you take its fiber at Y, and then we have some Y is another fixed point which is less than X, and so the condition is on which weights of the torus appear in, well, this complex. It's in cohomology, and so they should be contained in a certain polytope. So maybe I'll write it P Y. So this is a polytope, again, which is independent of the choice. But then here there will be some shift, which well, depends on technically on lambda, where lambda is in A. So what does this shift? How does the shift define? So I will define the shifts for so define shift for lambda in the actual Picard lattice inside my space V, and then extend by linearity. And to do this, so this corresponds to a line bundle, and then we can pick how it's called. I mean, just pick an action. So the line bundle automatically equivariant with respect to our torus. And so we'll just take, so there's some, for each fixed point, there's some weight by which it acts at this fixed point. You just take the difference of weights. So then shift is equal to weight of lambda y minus weight of lambda x. And then you extend by linearity. And yeah, probably that's all I want to say about this. But so this window condition. Yes, the claim is it's uniquely defined, and a harder claim is that it exists, which I think is due to Halper, Leisner, Davesh, and Andrei. Yes. No, that's not.
So how does the space distribute in
God knows, but
So you take all of them?
the condition is that, yeah, for all cohomology, this is true. This is,
Okay.
yeah, let's maybe not.
Is there any idea how to prove existence or what?
So, to me,
By, yeah,
for
the,
one-dimensional torus, this is in hyperleibniz thesis. This is how to semi-Stockholm decomposition of J.
yes.
The whole somehow the observation is that for very special interpretations, the one is for multi-dimensional torus. That's the essence of it.
Okay.
Okay, so let's, and yeah, I mean, it's, maybe it would be interesting to understand better the relation. I mean, there's some kind of new, apparently new property of Verma modules, at least in positive characteristic.
The dual of Fermat model, they kind of also have some kind of characteristic.
Yeah, for just the opposite. Huh? So,
Dual.
yeah, I think it's just the opposite Elkov or something like this, yeah. Okay, so maybe let's, and yeah, so Andrei discussed stable envelopes in cohomology, K-theory, and then even elliptic cohomology. And yeah, maybe I should say one word. So this characterizes the action on the K group of the derived category, and then somehow it's we need to check that the same happens for monodromy, and I don't know, maybe Andrei maybe will address it or will not address it, but anyway, so this can be obtained as some sort of a limit under degeneration from Andrei's result with Mina Aganagic, which applies to this fancier version, fancy elliptic version of this. Okay, so I want to talk about other things too, and so I want to actually return to the topic which was at the end of last talk, and so it's this central charges and perverse occurrences, and then in the end I need to get to the topic in the title, but this is named the canonical basis. So fortunately this notion was already defined by Ivan, and so recall that for a derived equivalence for abelian categories A and B, and then the equivalence dVA, dVB is a perverse equivalence corresponding to some filtration corresponding to filtrations by Serre subcategories AI, BI. Well, if the associated, well, if the functor is compatible with the filtrations and dir I of phi with shift by I, or maybe minus I don't know, is T exact. So we kind of get this abelian equivalences on graded pieces, but altogether we get something U, you know, if going from A to B. And so I want to present a funny way to build a filtration by Serre subcategories on an abelian category. Suppose that so let A be an abelian category. And suppose we have some zeta, a central charge, is a polynomial map from real numbers to the dual space to the K naught, well, tensor R, which has this property that, which has a positivity property such that zeta of t is positive. So you can take zeta of t paired with m is positive for m and a different from 0, and t close to positive and close to 0 in 0 epsilon, for some epsilon. Then we define a filtration, then let AI be the set of M such that the polynomial zeta of t, so that the function t goes to zeta of t m, has a 0 at 0 of order at least is, yeah, maybe this function is, how does people write it? O of t to the I. In other words, it has small o of t to the I. In other words, has 0 of order at least I. And the point is that this condition shows that this is a Serre subcategory, because if a sum of two positive functions grows, is like that, then each of those functions is like that. So okay, so this is a funny little definition, and so let me describe the next ingredient in this picture. Again, this is something I think, strictly speaking, is completely figured out only in T star G mod B case. And so to formulate this step, we need. So basically, what I want to explain is how this, derived equivalences between abelian categories for different alcoves, how they interact with T structure. So some derived equivalences, but how what happens to the abelian category. And for this, I need to introduce the central charge. So which will so define the polynomial map Z from our space V to K naught of our category, and so so we have this star. So this is a polynomial map. So it will be characterized by
What is V?
V is our H2, I mean the space of Kähler parameters. And so I will say what it does to lambda in the lattice. So it goes to the functional, which sends f to the Euler characteristic of f tensor of lambda. And of course, by Riemann-Rochmanov is a polynomial, which you can write down explicitly. So this is Euler characteristic. And the next sort of expectation, so claim, which is again a theorem for P star G mod B. So which is in our paper with Ivan from this last year. And it says that so it says the following. So it actually characterizes an equivalence of the following sort. So you take an Elkov and you fix a phase, and you go to the opposite Elkov with respect to this phase, crossing in a positive direction. So I guess crossing in the positive direction, positivity is determined by this choice of x, choice of points at infinity. And so with all these choices, it's what I want to say is that so this functor corresponding in this pink functor is a perverse equivalence where the perversity for the filtration is above where z is just a restriction of z to a line to a generic line passing through this point. Zeta is line through the phase. And so there are several remarks one needs to make here. So first of all, this is related to questions of representation theory. So and questions of the form, questions like Oettinger's conjecture, and I think the conjecture was kind of based on some ideas like that. So we can identify. Yes.
I'm very bad with abbreviations.
Representation theory. Representation theory.
Okay, fine.
So,
Today,
huh? Okay, so the category, this abelian category A, well, if you pass to field of positive characteristics, so we kind of by construction, it's going to be equivalent to the category of representations of some what I called or Y quantum. Well, modules with central charge, with generalized central character 0, and maybe I'll write it this way: O lambda quantum. Lambda, where lambda is an integral parameter and lambda is in, so say, PA. And so you can look at this invariant of a representation, and so can check. And so recall this picture that we have these different points in the LCOF, and the abelian categories for. Well, lambda is a parameter of quantization, and it's required to lie in the LCOF. And as long as it satisfies these requirements, all the abelian categories are identified. So one can sort of look at the basic invariant of representation, just dimension, and dimension. So you can think of it as a function on this lattice. And it turns out that it's going. And also, well, we kind of glossed over this a little bit, but things can be identified for different coefficient fields. So you can think of it as a function of lambda and p. And it turns out that the dimension, so for m in this category, we have this polynomial Pm of lambda comma p, or maybe I call it d, which whose value for a given lambda and p is equal to dimension of, well, m lambda p in the obvious notation. So as I said, this is polynomial, and I can well try to understand. The basic features of this polynomial, for example, is degree in p. And so notice that for example, when this degree is equal to 0, this is exactly the situation where when the representation comes from characteristic 0. So we can want to count irreducibles for a given degree of d m, irreducibles, whatever, L with L of lambda p, a degree in p. And notice that for degree equal to 0, so degree equal to 0, one can show that this is equivalent to saying that L comes from characteristic 0. So in particular, this problem contains the problem of counting finite dimensional representation in characteristic 0, and this is expected and proved in the T-star GMLB case that well, in this situation, when you have finitely many fixed points, so you have category O defined, then this actually matches the count of irreducibles in category O with given dimension of support. So for enveloping,
I thought this is more or less a theorem.
okay, and yeah, so this is related to. So again, so this corresponds to count.
So sorry. So
Of
is degree 0 even if L is interdimensional in characteristic 0?
what?
And you said that they expected that
Finite dimensional.
L is L finite dimensional or interdimensional?
finite dimensional L correspond to degree equal to 0.
Ah, okay.
And degree equal to something, to
Are these polynomials related to all Tony Joseph?
yes, they are related. They are related. But yeah, maybe let me not explicitly answer this, but yes, they are closely related.
May I make
Yes.
quick remarks? So first of all, this claim is more or less a theorem in the case of finitely many fixed points.
Yes.
And in the general case, we do know that the equivalence is perverse, but we were not yet able to identify the filtration.
Yeah. Yeah.
But
that's
in the group case, that many people do.
Uh-huh.
These polynomials do they coincide with Joseph?
Can you say it quickly? But I mean, I think one is a small linear combination of the others. But I can describe it to you. But I think that's true. Number of objects with support in category O over C.
Well, let me ask
With support of dimension A. Yes.
let's do the very stupid one. Let's take the ultimate product.
Yes. Yes.
Can we get something in characteristics
Uh,
has kind of the property having characteristic P?
I actually
Is there
thought
a way
about.
to describe these characteristic zero objects
Yeah.
which produces this structure?
I actually thought about this, but then Vanya found a better method, so I didn't try it. But maybe we should get back to this idea. Okay. So yeah, that was the first remark. And the second remark is so relation to some relation that to things in algebraic geometry. And this is maybe will be mostly hand waving, but so relation to bridge instability conditions. So this was kind of this partly the motivation for it, and initially I just thought that this will be literally the same, meaning that it will produce some submanifold in the bridge instability. Now I no longer think so. So there is actually a new concept that we define. So there is a concept real variation of stabilities, but so since there is no so this is in the paper of Renan or myself and Mirkovic. Let me, like, without maybe writing much, let me try to indicate the idea. So Bridgeland defined this concept of stability manifold for a triangulated category, and a point in the stability manifold is a T structure and a linear functional some zeta in K naught of our category star. And there is this axiom that the central charge of an object in the abelian heart lies in the upper half plane. And then there is this first kind of key theorem in this theory is that this local isomorphism theorem, which basically means that if you vary this kind of strange continuous in part of the data a little bit, then you can vary the T structure uniquely. And then the way it works is that, so in the simplest cases, so you say that if the category is something like what we like, so it has finitely many reducible objects and all have finite length. And then, well, there is some central charge of some irreducible object, sort of well, while it's running in the upper half plane, nothing is happening. But suppose it's, it wants to get out of it and cross to the other side, and then all of a sudden, after it has crossed, it started violating the condition, and then we replace it. So this is L, and then we kind of replace L by L of 1 to get it back sort of to the upper half plane, so to send it here. And then we modify the T structure accordingly. So this is a simple, this is also called tilting of a T structure, but it's an example of a perverse equivalence, the easy one where just this shift by 1. Now, so here, well, there is a little discrepancy that this is, my central charges are real, but let's multiply them, say, by I, they will lie in the upper half plane. But now, well, there is elementary complex analysis tells us that if we have a polynomial which vanishes at degree I, and if the variable goes from r plus to r minus, then the value of the polynomial crosses the boundary of the upper half plane I times. So from this kind of considerations, it tells us that we should be shifting these objects by I. So it's all nice at the level of heuristics, but actually if you want to try to make an argument out of it connecting the two settings, then you run into difficulty because this procedure is sort of it's not robust, meaning if you shift the objects one by one, it very much depends on the order, etc. So in some easy case, in this paper of ABM, like in this T star G mod B case, we do make some sort of connection. But it's a easy situation where basically all shifts are by one. So I came to conclusion that this should be like a different axiomatics, which implements the same heuristics, but really different. Okay, so this is it. And so in the and so one last remark here, remark 3. And so notice
the kind of bridging language is not sufficient because it doesn't say order.
It doesn't contain monodromy. So monodromy in a way has to be constructed by hand. So yes, and so the last remark here is so relation to the quantum connection. So as I think had a chance to say last time, maybe, so the central charge can be thought of as a flat section of a trivial limit of a kind of boring trivial, trivial, not just identity zero, but uninteresting specialization of the connection and well, I don't want to spend much time on it, but there potentially is some sort of phenomenon from just differential equations which I don't understand. So basically we have a family of connections, so we specialize it to the trivial value of parameter, have this section, and so most of the singularities disappeared. But then we have some kind of a residue of this interesting story, because in these regions, in these alcoves, we have these bases of sections, and these sort of, there are some something sort of singular still happening on these walls, but in a different sense. So the solution is going to have a zero coordinate in these bases on the wall. So again, so since there's no real theorem here. I don't want to spend much time on it, but I just want to make this sort of point.
What do you want? You don't
I want some construction from a theory of differential equations, which would, from a family of differential equations degenerating to something trivial. I want to construct, well, ideally I want to construct a basis with these properties that, you know, have some. Had some speculation that it looks like a Hodge structure, but it's not. I can't really argue convincingly this is the case. Okay, so in the remaining 7 minutes, I want to address the second main topic of the series of lectures, namely the canonical basis. And so so in a way, my kind of original goal in going into these projects was to check that I want to check that the basis of irreducibles in A is a canonical basis in the sense of cardinalistic theory. In this KT, well, in the K group of our category, in this in the fiber of my local system of A, which is again identified with KT of X C prime. And again, so this is a theorem of myself and Mirkovich, and based on joint work with Romanian also for T star G mod B. So there are two kind of difficulties, and the first less serious ones is that I don't know the definition of a canonical basis. But this is okay because one can still make the conjecture without giving the definition. Namely, in that case, well, in that case, the canonical basis was defined by Lustig, and the theorem, after some formal reductions, really well, I mean, following ideas of Zorgel and other people, I guess Victor and Sasha Beninson, so the theorem is reduced to the following conjecture, which can be stated, which is easy to state in general, but not easy to prove. So conjecture is that so that this category, that AA, is has the Koszul property, and this is not to be equivalent to positively graded. So what do I mean? So again, A is a module over some algebra, which let me call it R. That's well-defined optimal equivalence. In fact, maybe I didn't mention it, but I should have that. It all comes from some tilting vector bundle, and RA can be thought of as the, well, opposite, as Ivan pointed out, algebra to endomorphisms of some E A, and so this is a vector bundle on XC, tilting vector bundle on XC, and again, I indicated a little bit, some of its properties last time, so it can be characteristic P, it can be in the formal neighborhood of special fiber, it can be constructed splitting bundle of this quantization, etc., etc. And so at this point we should concentrate, think of, this kind of action of GM from the definition of symplectic resolution, so the one which dilating the form. So consider C star acting on XY, dilating the form. So it's easy to show that EA can be, so by just some rigidity, EA sort of can be given a C star covariant structure. So and then this equips, so then RA gets a grading, and the content of the conjecture is that conjecture says that this grading can be arranged so, there's some ambiguity in this choice of equivariance, can be chosen so that RA less than 0 is 0 and RA 0 is semi-simple. And then by an easy argument that I learned from Kaledin, then RA is automatically a Cauchy quadratic algebra. So yes, so yes.
It sounds that the best way to think about canonical basis comes from Rukier codification.
Yes, yes, but again, so of course this should be related to the, this should be a canonical basis for this algebra G of Q that Andrei and Devesh constructed for quiver varieties. It's just that I think people have not. I have some ideas of what should go into the definition, but I think the definition has not been written down. In fact, let me just make this remark that there is even the canonical bases lead to combinatorial structures such as crystals, and even that part is interesting and new. And there is some in the very, very special case of the Hilbert scheme, when the basis is indexed by partitions, it leads to interesting combinatorics. And so I just want to give this reference. So some of the, I guess the very first steps in this direction have been done by my students. So combinatorics for X being the Hilbert scheme of points, and so that the irreducible syntax by partition. So there is a paper on the archive by Demarkis and so Galina Dobrovolska has also some results about this. And let me maybe just finish that, some approach to proving it. In this case, it has been proven by relating things to perverse sheaves on loop spaces. And there is, at least in this very special case, there is also an approach that was there for some time, but I mean I think we're working on it again now, and maybe we'll finish it at some point. So there's an approach.
Either we finish it or it finishes us.
Yes. So there is a similar approach based on Langland's duality for elliptic curve, and in general, for general quiver varieties, there are only tentative ideas. Which, but yes, so the point I want to make is that there is a known here and potential in other cases relation to topology of loop spaces. So that's another direction that's interesting to explore, and so maybe that's a good time to stop. Huh?
It's known in GMRP, and it's known for Hilbert scheme, or it's not known?
Well, even for Hilbert scheme, I mean, it's not known.